Hello, and welcome to Linear Algebra. This is lecture 10, and our topic is elementary matrices. So, last time, we talked about matrix multiplication. And how the composition of linear maps leads us to define the multiplication of matrices. And we saw how there were at least three different ways of thinking about matrix multiplication, including that you can think of the product of A and B as the matrix whose columns are the products of A with each of the columns of B. This time, we're going to talk about row operations and Gaussian elimination and how that relates to matrix multiplication. Okay, so it turns out the relation is very direct. It turns out that row operations can be carried out via matrix multiplication. So let's see some examples. Just see what I'm talking about. So our first row operation is to add a multiple of one row to another. So suppose I start with the matrix, let's just use 3 by 3. Suppose I start with this matrix, and then I multiply an arbitrary matrix of size 3 by 3. Okay, so remember the way you find this is, for example, I take this row times this column, and I find A. I take this row times this column, find D. I take this row times this column, and I end up with 5A plus G. And then similarly, here I would get B, E, 5B plus H, and here I would get C, F, and 5C plus I. And now we stare at this, and we notice that if you start with this matrix and you add 5 times this row to this one, then this is what you end up with, right? And notice that the matrix we multiplied by is start with the identity matrix and then add 5 times this row to this one, right? We're going to give this a name just to make it easy to work with. This will be denoted P531. Very catchy name. But the 5 corresponds to this 5, and it was to row 3 from row 1. Right. Our second row operation was to multiply a given row by some non-zero scalar. So let's consider this matrix. Okay. So you'll notice that this matrix is obtained from the identity matrix by multiplying the second row by 5. And if we do this product, right, so again, let's say to find the first element, I do this row times this column. To find the second one, I do this row times this column. To find the third one, I would do this row times this column, and so on throughout the matrix. And notice that indeed, the matrix we ended up with is what you end up with from this matrix by adding 5 times, by multiplying this row by 5. Okay, this gets its own catchy name. This is going to be the matrix Q52. And our final row operation is to switch the order of the rows. So we've already seen in one of our previous examples that you can do this by matrix multiplication. Well, we saw it at the level of vectors, matrix vector multiplication. But since matrix multiplication can be thought of as just doing a bunch of matrix vector multiplications, it follows that it's also true for matrix multiplication. So if you work this out, you get A, G, D, and so on. So B, H, E, C, I, F. So it is indeed the effect of starting with this matrix and switching the order of these two rows. Right? And we're going to refer to this matrix as R2, 3. Right? So let's write out what we noticed. In each case, we carry out the row operation on the identity matrix, then multiply with A, and the result is the same as carrying out the row operation on A. Okay, so let's go ahead and define this in general. Okay, so let's give ourselves two numbers, I and j, between 1 and m, and a scalar in some field, and define matrices. These are going to be in matrices of size m by m. By, okay, first, if I is different from j, then we're going to define p c I j to be, okay, so let's write it out. So you would have, well, so this is going to be the matrix you get from, so it's going to look just like the identity matrix, except somewhere there's this C. Right, so let's put a 1, C, zeros. So it's just the, so let's write out. This is the result of adding C times the jth row to the ith row of the identity of size m by m. Right? For C not equal to 0, QCI. Right? So this one's easier to write. This one just has, looks just like the identity, except it's somewhere you multiply the ith row by C, right? So it looks just like the identity. On the diagonal, you have ones everywhere, except for a C, which occurs on the ith spot. And this is the result of multiplying the ith row of the identity by C. And then finally, for I different from j, we have the matrix Rij. And so this looks like the identity matrix, but somewhere you've changed the order of 2 rows. So this is the result of switching the ith row of the identity with the jth row. Okay, and collectively, these are known as elementary matrices. Okay, so an elementary matrix is any matrix you can obtain from the identity by performing one row operation. Okay, and a simple computation, just like the ones we carried out in the example before the definition, gives you this theorem. I'll let you read the details in the book, or even better, work this out for yourself. For any m by n matrix, PCIJ of A, this product is the result of adding C times the jth row to the ith row of A. Right? QCI A is the result of multiplying the ith row of A by C, and Rij A is the result of switching the ith and jth rows of A. Okay, so I encourage you to try to prove this yourself. It's not hard. It's just like the examples we did in the 3x3 case. It's just working with the notation for a general matrix product. Okay, and once we have that theorem, then an obvious consequence is that we can carry out Gaussian elimination on a matrix A by multiplying it with a bunch of elementary matrices. Right, because we can carry out each individual row operation by multiplying with an elementary matrix. So although that's pretty obvious, it's really useful. So let's go ahead and state it formally as a theorem. So one way of saying this is that given any matrix of size m by n, coefficients in the field, there is a matrix B also of size m by n, so same size as A, in reduced row echelon form, and elementary matrices, say E1 through EK. These are square matrices of size m by m, such that B is equal to E1 times ... up to EK. Actually, let me put them in the opposite order. So let's do EK minus 1 ... E1 times A. So that you start with the matrix A, And then you do the first row operation, then you do the second row operation, and so on. You've done the kth minus 1 row operation, you do the kth row operation, and when you're done with all those row operations, you obtain the matrix that is in reduced row echelon form. Okay, so this theorem, the proof we've basically already done. This is just a restatement of the fact that Gaussian elimination lets you put any matrix in reduced row echelon form. Okay, now here's an easy fact. Every row operation can be undone, right? You can always do another row operation to undo it. So what does that mean about elementary matrices? It says that all of the elementary matrices are invertible. Right? In fact, it says also that their inverses are also elementary matrices. So, as we already said, every row operation, this follows because every row operation can be undone by another row operation. So it's easy enough to just write down what the inverses are. If you start with the elementary matrix P Cij, then its inverse is to do P minus C ij. If you start with the matrix QCi, then the inverse is to do QC inverse. Yeah, C inverse I. Right, so C is an element of a field, right? And for the second row operation, we require that C be non-zero. And every non-zero element of a field has a multiplicative inverse. And then finally, if you switch the rows I and j, you can undo that by switching the rows I and j back. So this third type of elementary matrix is its own inverse. Okay, so now we could state this theorem differently by just putting all the elementary matrices on the other side by taking their inverses, right? So we can restate the theorem as saying, given any m by n matrix there is a matrix B of the same size in reduced row echelon form, and elementary matrices, let's call them F1 through Fk, right? So these are going to be of size m by m, such that A is equal to F1 dot 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 Fk times B. Right, so indeed, so after all, if we have B equal to Ek minus 1 dot 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 E1 times A, then, okay, now we know that each of these matrices is invertible, and we know that the product of invertible matrices is invertible. So that means that all of this is together is an invertible matrix. So I can write A as this whole matrix inverse times B, right? The inverse on the left. But we know that the inverse of a product is the product of the inverses in the opposite order. So this inverse is equal to E1 inverse, E2 inverse, dot, 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 Ek inverse times B. And so just take F sub I to be EI inverse. Right? Because we know that, and it's an elementary matrix because we know that the inverse of an elementary matrix is an elementary matrix. Okay, so this is just an equivalent theorem. You can start with a matrix in reduced row echelon form and perform row operations on it and end up with whatever matrix you started with. Okay, great. So row operations. Now that we can write them as matrix multiplications, they give us a useful way to invert a matrix. Okay, so why is that? Well, let's combine the following two facts. Okay, so the first fact is that to solve AX equal to B, we form the augmented matrix A with B added, and then use row operations to put it into reduced row echelon form. And then our second fact is that the jth column of the product of two matrices is A times the jth column of C. Okay, so we're going to combine these two facts. So fact 1, fact 2, to get an algorithm for finding A inverse if it exists. And actually, this algorithm will tell us whether or not A inverse exists. Okay, so what do these two facts have to do with each other? So, well, indeed, if A times C is equal to the identity, and you write C as the matrix whose columns are C1 up to Cm, then AC equals the identity says that then AC, this would have columns AC1 through ACM. And we want this to be equal to the identity, so the identity, but the identity has columns E1 through EM, right? So to say that AC is equal to the identity is really to say that the columns of C satisfy ACJ equals EJ, right? Where the EJs, of course, are the standard bases of Rn. Remember, that means that EJ is a vector whose coordinates are all 0 except for the jth coordinate, which is equal to 1. Okay, so inverting a matrix, right, solving this for a matrix C is the same as solving a bunch of linear systems of equations. And we know how to do that. We do that by using reduced row echelon form. So here's our algorithm. This will determine if a square matrix A is invertible, and if so, find the inverse. So it's a very useful algorithm. Okay, so here's what you do. First step, form the augmented matrix. We put A on the left, but now we're going to augment it not just with one vector, but with the whole identity matrix. And then put it into reduced row echelon form. Okay. Step 2. If the reduced row echelon form looks like the identity matrix on the left and then some other matrix on the right, then A is invertible, and the inverse of A is equal to B. On the other hand, so step 3, if the matrix on the left half of the reduced row echelon form is not IM, then A is singular, right? So singular is where we call a matrix that is not invertible. Okay, and the proof that this works is exactly this observation we made above about how finding the inverse of A means solving these systems of linear equations. And here, all we're doing is solving them all at the same time by doing because the row operations that you have to do on A, you have to do regardless of how you augment it, right? So you might as well do them all at the same time. And when you do, you end up with the inverse if you ended up with the identity on the left. Okay, but notice this is a really nice observation from this algorithm. Notice that the reduced row echelon form of a matrix is the identity if and only if that matrix is invertible. Okay. Now, we've seen before, when talking about fields, for example, and I think also for matrices, that if you have a matrix and it has a left inverse and it has a right inverse, so it has a matrix that when you multiply it on the left, you get the identity, and there's some other matrix so when you multiply on the right, you get the identity, then those matrices actually have to be equal and they have to be the inverse. Right, so we didn't state it quite like that for fields because of course for fields, matrix multiplication in fields is commutative, but the proof we gave that the inverse is unique, if you look back at it, will actually show you only need for the one element to be an inverse on the left and the other element to be inverse on the right for that proof to work. However, for matrices, something stronger is true. If you have an inverse on one side, then you also have an inverse on the other side. Right? Of course, for a field, if multiplication is commutative, then having an inverse on one side implies having the inverse on the other side. But when you're working with things where multiplication is not commutative, this is not automatic, right? But it's true for matrices. Right, so for example, if we were working with infinite dimensional spaces, for example, the space of sequences f infinity, then it's very easy to find operators, linear maps, that have an inverse on one side but not the other. So for example, in some previous lecture, we gave an example of the shift map on the space of f infinity of sequences. As an exercise, check that if you have sequences, that there are shift operators that have an inverse on one side but not on the other. Okay, but for matrices, that doesn't happen. If B times A is equal to the identity, so if B is a left inverse, or if A times B is equal to the identity, so B is a right inverse, then actually A is invertible and B is the inverse of A. Okay. So this turns out to be easy to prove. We just have to remember that matrix multiplication and inverting has to do with solving systems of linear equations. So if B times A is equal to the identity, then we can always solve AX equal to B uniquely. Right? Because if B times A is equal to the identity and you have this equation, then you just multiply by B on the left on both sides of the equality. Right? So X is equal to capital B times lowercase b. Okay. But if this has a unique solution for every B, so let's write this out. Hence, if I augment the matrix B, this has a pivot, well, the reduced row echelon form. The reduced row echelon form of this has a pivot in every column except the last one, right? So the reduced row echelon form of A is the identity. So by the algorithm, A is invertible. Right? And then here's the proof I was just talking about. Once you know that A is invertible, then you can write B as B times AA inverse. And then B times A is equal to the identity. So this is just A inverse. Okay, so that takes care of the first case if B times A is equal to the identity. What about if A times B is equal to the identity? Okay, well, if A times B is equal to the identity, then we've just shown, right? So just replacing the order, we've just shown that B is invertible. And A is equal to B inverse. But that means that B is equal to A inverse. And so we're done. Okay, let's do an example. See how this works. So let's invert the matrix A given by 3, 2, 1, 2, 3, 1, no, 2, 3, 2, 1, 1, 3. So this is the matrix from the system of equations from ancient China that we saw in the first lecture. Okay, so the algorithm is to find the reduced row echelon form of A ... IM, right? So you would start with 3, 2, 1, 2, 3, 1, 1, 2, 3, and you'd augment this with the identity, right? And now we'd start with row operations. So just like before, let's start by switching the order of these two rows. All right, so I end up with 1, 2, 3, 0, 0, 1. Then nothing happened to this row, 0, 1, 0, and then this row, 3, 2, 1, 1, 0, 0. Right. Next, we would use this pivot to clean up the rest of its column. So nothing happens to this row. This row would end up as 0, minus 1, minus 5. And here's 0, 1, minus 2. This one would end up with 0, minus 4, minus 8. And here 1, 0, minus 3. Okay, then you would multiply this row by minus 1. This would give us a pivot here of 1. And then we use this pivot to clean up the rest of its column. So that means that the second row is going to end up as 0, 1, 5, 0, minus 1, 2. And you can work out that the first row after you've cleaned up the column is like this, 0, 2, minus 3. And over here, 0, 0, 12, 1, minus 4, 5. All right, and next you would divide this row by 12. That would give us a pivot here of 1. And then we would use that 1 to clean up the rest of its column. And you can check, assuming I did the computation correctly, that you end up with here 7 over 12, here minus 4 over 12, minus 1 over 12, minus 5 over 12, 8 over 12, minus 1 over 12, 1 over 12, minus 4 over 12, and 5 over 12. Right? And we ended up here with the identity matrix, and we ended up here with what has to be A inverse. Right? So there you go. We've inverted the matrix just by doing row operations. Just putting a large augmented matrix into reduced row echelon forms. Okay, let's just restate this algorithm a little bit with multiplication by elementary matrices. So in terms of elementary matrices, if A is invertible, then there are elementary matrices such that the identity is equal to EK times EK minus 1 dot 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 E1 times A. Also, the algorithm says that if we start with the augmented matrix A and IM and multiplying by EK dot 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 E1, well, that just performs the row operations that put this matrix into reduced row echelon form. So that means that we end up with IM on the left and A inverse on the right. But since we're doing this just by multiplication by this matrix, we notice that if we had started instead of augmenting with the identity, let's say I augment with some other matrix B. This doesn't even have to be a square matrix. I can augment just any number of columns I want that are of the correct size. And then multiplied by EK to E1, or if you like, put it into reduced row echelon form, then we would have ended up with IM on the left and A inverse times B on the right. Okay, so if you need to figure out the product of A inverse times B, you don't actually have to find A inverse and then multiply it by B. You can start with this augmented matrix, put it into reduced row echelon form, and you find in one go A inverse times B. Right? Notice that's what we do when we solve a system of linear equations. If A happens to be invertible and you augment just with one single column, then the answer you find, which the unique answer in that case, is A inverse times B. Okay, so that's the end of the lecture, but now I'll give you some historical context. So feel free to skip this if you like and stop listening now. Today I thought I would mention a bit about Gauss. He's come up before. The algorithm of solving a matrix by row operations is known as Gaussian elimination in his honor, though as we mentioned in the first lecture, he was not the first person to come up with it. Gauss was alive from 1777 to 1855. He is known as one of the greatest, if not the greatest, mathematician ever. His parents were not very highly educated. His father was a bricklayer, and his mother was apparently illiterate. And he seems to have started doing mathematics before he was really able to talk. So at the age of 3, the story goes that his father was trying to figure out how much he owed his employees and was doing the arithmetic operations out loud, and Gauss actually stopped him and corrected him. 3-year-old kid. When he was a young boy in school, so apparently around 7, the teacher, had a bunch of students of lots of different ages and wanted to keep them occupied for a little while. And so he told them that they had to sit there quietly and just add up all of the numbers between 1 and 100. And the story is that Gauss just wrote down a single number, 50-50, and turned it in. And the teacher was annoyed that this kid was not doing what he was supposed to be doing, and said, okay, how did you come up with that number? And Gauss told them that actually it was really easy. If you want to add up the numbers from 1 to 100, then what you should notice is that the first number plus the last number add up to 101. Then if you move up by 1 and down by 1, so the second number and the next to last number, 2 and 99, they also add up to 101. And then if you keep going in pairs like this, so 3 and 98 add up to 101, and 4 and 97 add up to 101, and so on. So really, you just have 50 pairs that add up to 101. So you just need to do 50 times 101, and there's the answer, 50-50. So we know this happened because Gauss loved to tell the story, apparently. And one of his best friends wrote a biography of Gauss soon after he died, where we find this story. But also because the story had a consequence. This teacher, much to his credit, did not just get annoyed at the student having come up with a workaround to this task he had given him, but instead, a little while later, assigned one of his graduate students to just teach Gauss math. And also, as a consequence of this and Gauss's interactions with this graduate student, he was brought to the attention of the local duke. Now, Gauss was growing up in Brunswick, so it's the Duke of Brunswick, which is now part of Germany, sort of central Germany now. And the Duke agreed to pay a stipend for Gauss, including all of his schooling, so that Gauss could just devote himself to thinking about math. So Gauss did, and he did very well. So one of the things he that when he got his PhD in mathematics at the age of 17, he wrote his thesis on the fundamental theorem of algebra. This is something we will use later. The fundamental theorem of algebra says that if you have a polynomial and all of the coefficients are complex numbers, then the polynomial has at least one root, and there's at least one complex number that when you plug it in gives you 0, and hence it's easy to show it has exactly m if you count with multiplicity, if the degree is m. He starts his thesis by saying this is a really important theorem. It's been talked about for thousands of years, but nobody has ever given a proof. Here are 4 different proofs. And then he gives you 4 different proofs of the fundamental theorem of algebra. There's a fun story that in 1801, so the first year of the 19th century, on the 1st of January, 2 things happen. Hegel, a very important philosopher who was very arrogant, was giving a talk where he said that these astronomers who keep looking at the sky and trying to find new things are being very silly, because anybody who knows anything about philosophy would know that there are going to be exactly 7 heavenly bodies, and we've already found 7 heavenly bodies, so they're not going to find any more. Right, and the other thing that happened that day was that they found another one. They found a planetoid called Ceres, after the Roman goddess of agriculture, farming, the mother of Persephone. And so there was a race to try to figure out what the orbit was. The problem was that they had found it very close to the sun. So they were able to take observations for a little while, but soon it was going to be covered by the sun, and then it was going to be a while before its orbit would take it to the other side of the sun so that people could start observing it again. And so the question was, okay, months from now, when it makes it to the other side of the sun, from the perspective of the Earth, where will it be? And lots of people wrote out proposed solutions, and Gauss, who was completely unknown at the time, proposed a solution that ended up being very different from what the other people were proposing, but ended up being exactly right. So this was seen as an amazing feat of computation, especially back then when there were no computers, no electrical computers. To do that, he seems to have come up with a method called least squares approximation, which we will come back to. It'll be in a class much later in the semester. He also came up with non-Euclidean geometry, hyperbolic geometry especially. So this is, so as you know, Euclid's elements develop the geometry of what seems to be the real world in this very systematic way, with axioms and definitions, and that leads to propositions, lemmas, theorems, and so on, and everything is very carefully structured. But there was one of the postulates, so there were things that didn't seem as natural as axioms, but were still going to be just assumed, called postulates. And the 5th postulate said that any line, given any line, and any point not on that line, there is a unique line through that point that is parallel to the line you started with. So meaning that it never meets it, they don't intersect. So it turns out people thought for a long time that maybe you could deduce that postulate from the other axioms and postulates, and that it would be a theorem instead. But all of their efforts had failed. And Gauss was one of the first people to realize that the reason it was failing was because it wasn't true. You could develop a completely consistent system of geometry where that postulate was not true. So in fact, there are 2 ways that you could have it fail, so that given a line and a point not on that line, there are no parallel lines through that point, or there's more than one parallel line through that point. Both of them work out. So the case of there is no parallel line through that point is known as spherical geometry or elliptical geometry, and the case where there are many is known as hyperbolic geometry. And that's one of the geometries that Gauss worked out. Another good story about Gauss was in 1806, the French occupied Brunswick, and a general came by to see that Gauss was okay, and said that he had been sent by a lady in Paris, a family friend of his, known as Sophie Germain. And so Gauss was very surprised. He had never heard of this Sophie Germain, but it was very nice of her to have sent this general to check that he was okay, and he was okay. So thank you. He later it turned out that he did know Sophie Germain, but he knew her under a different name. She had been corresponding with him about some of his studies on something called number theory for years, but under the name Monsieur Leblanc. And so Gauss wrote a letter. We know he had already been very impressed with what Monsieur Leblanc had been saying about number theory, which was one of Gauss's specialties. And he wrote this very nice letter to Sophie Germain after she confessed to him that she had been writing to him under an assumed name. And here's a snippet from it translated in Wikipedia. He says, "How can I describe my astonishment and admiration on seeing my esteemed correspondent, Monsieur Leblanc, metamorphosed into this celebrated person? When a woman, because of her sex, our customs and prejudices, encounters infinitely more obstacles than men in familiarizing herself with number theory's knotty problems, yet overcomes these fetters and penetrates that which is most hidden, she doubtless has the noblest courage, extraordinary talent, and superior genius." So that's a nice story. Unfortunately, they never actually met. Gauss did not travel very much from Germany, the University of Göttingen, where he was working. Another thing that happened with this French occupation of Brunswick, so unfortunately the Duke of Brunswick, Gauss's not mentor, but patron, Gauss's patron, had decided to challenge Napoleon on the field of battle, and that was not a very bright thing to do. So the Duke was dead, and Gauss no longer had this stipend. So he did other jobs. He carried out a surveying expedition of the nearby region in Germany. In fact, his observations from that apparently inspired his work in non-Euclidean geometry. He also ended up working as the director of the observatory in Göttingen. And together with Weber, he did a lot of work in electromagnetism, including developing an early telegraph. Because of this work in magnetism, the international unit of magnetic induction is known as the Gauss. Also, perhaps because of that, when the widow's pension in Göttingen was running low on money, Gauss stepped in to help them with their finances, to help them investing their money. So he learned about finance, and he found it all very easy, and he ended up doing very well for himself, investing in the stock market, his own money, as well as the widow's pension. Okay, very good. We'll stop there and pick it up from there next time.